Évariste Galois was killed in a duel when he was only 20 years old. Yet by that time, he had already come up with one of the most influential mathematical theories of his time. For thousands of years, people had searched for a solution to a generic quintic or degree 5 polynomial. Galois' novel insight was to look at structure-preserving permutations of the roots. It is these permutations that eventually gave rise to the modern mathematical definition of a group. Ubiquitous examples of permutations are symmetries, and we will motivate the structure of a group by looking at symmetries of geometric objects. Take a book and lie it down in front of you. Think about how many ways you could pick it up, move it around, and place it back in the same place or footprint. With a little thought, we can see that there are only 4 possible options. The book can end up unchanged, rotated 180 degrees, flipped across its vertical axis, or flipped across its horizontal axis. If we model the book as a rectangle, then we can see that there are 4 distinct symmetries. Next, let's discover all symmetries of an equilateral triangle. To help us keep track of what each symmetry does, we will color the vertices. First, we can leave the triangle unchanged. Let's call this the identity symmetry and denote it by 1. We can rotate the triangle counterclockwise by 120 degrees. Let's call this rotation R1. We can rotate the triangle counterclockwise by 240 degrees. Let's call this rotation R2. We can also reflect the triangle across its vertical axis, the one that goes through the yellow vertex and the center of the opposite edge. Let's call this reflection F1. We can reflect the triangle across the axis that goes through the red vertex and the center of the opposite edge. Let's call this reflection F2. Finally, we can reflect the triangle across the axis that goes through the blue vertex and the center of the opposite edge. Let's call this reflection F3. There are a total of 6 symmetries. Half of them are rotations. They don't change the orientation of the triangle. And half of them are reflections. They reverse the orientation. Let us explain what we mean by this. In the original triangle, counting from the top clockwise, the order of the vertices is yellow, blue, red. Each rotation preserves this order, but each reflection reverses this order. The yellow, blue, red sequence must be traversed in the counterclockwise direction. Observe that if we apply 2 symmetries in succession, the result is yet another symmetry. Let's figure out what happens when we apply one symmetry after another. This operation is called composition. To keep track of the composition of symmetries, we will record the results in a so-called Cayley table. The labels in the leftmost column correspond to the first symmetry, and the labels in the topmost row correspond to the second symmetry in the composition. Now, let's compute all compositions of the symmetries of the triangle. First of all, it is clear that composing with the identity symmetry doesn't result in any change. Next, R1 followed by R1 is the same as R2. So the composition of R1 with R1 is equal to R2. R1 followed by R2 is the same as the identity symmetry. So the composition of R1 with R2 is equal to the identity, denoted 1. Let's pause for a moment here. We will adopt the convention that symmetries are composed from left to right. In some other sources, the symmetries are composed from right to left, like the operation of composition of functions. Neither approach is right or wrong, but it's important to keep this distinction in mind. For those already familiar with group theory, our choice of convention implies our group actions will be right actions. We will stress this point in future videos in this visual algebra series when it matters. With this caveat out of the way, let's get back to composing symmetries of the triangle. This computation reveals several patterns. First, composition of symmetries is a binary operation on the set of all triangle symmetries. This means that composing two elements from the set of all symmetries results in an element from the same set, that is, a symmetry of the same object. Second, composing symmetries is an associative operation because each one can be thought of as a function that permutes the vertices of a triangle. And we know that function composition is associative. This is an important property because it says we don't need to use parentheses when composing more than two symmetries. One could say parentheses are permitted anywhere but required nowhere. Third, there is an identity symmetry. When composed with any other symmetry, the result is still the original symmetry. Fourth, each symmetry can be undone in the sense that there exists another symmetry that, when composed with the original one, yields the identity. In other words, each symmetry has an inverse. For example, An inverse of the rotation R1 is the rotation R2, and an inverse of any reflection is the reflection itself. These are precisely the properties of an abstract algebraic object called a group. A non-empty set G together with a binary operation, let's call it composition, is a group if the following three conditions are satisfied. 1. The operation is associative, meaning that A composed with B and then composed with C is the same as A composed with the composition of B and C for all elements A, B, and C from G. 2. There exists an identity element, let's call it E, such that E composed with A is equal to A composed with E, which is equal to A for all elements A from G. And 3. For every element A of G, there exists an inverse element, A inverse, in G, such that A composed with A inverse in either order is equal to the aforementioned identity element. In particular, the set of all 6 symmetries of a triangle, together with the operation of composition, forms a group. We will denote this group by tri for now. It is a particular example of a larger class of groups called dihedral groups, and we will talk about these groups in a future video in this series. Let's turn our attention back to the Cayley table. Notice that each row and column contains every symmetry exactly once. This is actually one of the features of a group. If a table of compositions does not have this property, then the given operation does not define a group structure on the set. Also, this table has a block structure with respect to rotations and reflections. This is because a rotation composed with the rotation is a rotation, and a reflection composed with a reflection is also a rotation. Do you see why? Here is a hint. Reflections reverse the orientation of the triangle. So reversing the orientation twice results in no change, and it is precisely the rotations that are orientation preserving. Composing a rotation with the reflection is a reflection because in the end, the orientation has reversed exactly once. This could be a good place to stop, but we are going to kick it up another notch. Let's show that it is possible to generate all symmetries of a triangle by using only one rotation and one reflection. To simplify notation, we'll denote by R the rotation R1 and by F the reflection F1. The rotation R2 is R composed with R, which we can denote as R squared. So we are replacing R2 with R squared. The reflection F2 is R composed with F. So we are replacing F2 with RF. Finally, the reflection F3 is R2 composed with F, which is R squared F. So by combining the rotation R and reflection F, we can construct all symmetries. We say that the group of triangle symmetries is generated by R and F. Moreover, these generators satisfy the following relations. R cubed is equal to the identity. F squared is equal to the identity. And FR is equal to R squared F. Incidentally, we just discovered a presentation of the triangle symmetry group in terms of generators and relations. In fact, this information is sufficient to reconstruct the entire Cayley table and hence the structure of the group. We can forget that R is the 120-degree counterclockwise rotation of a triangle and that F is the reflection across its vertical axis. We can view R and F as abstract actions that satisfy the given three relations. This may be hard to believe at first, but let's see how far we can get. We are going to erase the Cayley table of the triangle symmetry group, and we are going to start from scratch with only two elements, R and F. We'll pretend that all we know about these elements is the three relations they satisfy. Like if the men in black used a flashy thing on us and erased our recent memory. Every group must contain an identity element 1, so let's add that to the list of the group elements. We can compose R with R and get a new element of the group, R squared. We add R squared to our growing list of elements. Composing R with itself 3 times results in the identity, because this is one of the given relations. This is also the same as composing R with R squared in either order. Any longer word in R will reduce to the identity to R or to R squared. For example, composing R squared with itself is equivalent to 4 copies of R. 3 copies of R is the identity, and the identity composes with any element in a trivial fashion. It follows that R squared composed with itself is equal to R. Composing F with itself yields the identity due to the corresponding relation. Any longer word in F will thus reduce to either 1 or F. Composing R and F produces a new group element, as does composing R squared and F. Next, let's compose F and R. We have a relation that says this is equal to R squared F, and hence we don't get a new group element. To compose F and R squared, let's think of this as FRR. According to a relation, FR is equal to R squared F. Applying this relation again, we replace the second instance of FR with R squared F. But we already know that R squared composed with itself is equal to R, and thus F composed with R squared reduces to simply RF. Now that we have gotten a hang on how relations can be used to compute various compositions, we will quickly compute all remaining compositions. Pause this video, if necessary, to figure out how each step of the computation was performed. Keep in mind that we were flashy-thinged, and so we don't remember that R and F can be interpreted as certain symmetries of a triangle. We also know how composition with the identity works in every group, so we can complete the Cayley table. This is the same table we obtained by composing the symmetries of a triangle. In case this thought hasn't occurred to you, we just discovered a superpower of mathematics. Mathematicians are immune to the flashy thing. Even when our short-term memory was erased, that is, we forgot that the elements of the group corresponded to the symmetries of a triangle, we still managed to reconstruct the group structure using a different approach, that of generators and relations. How cool is this? Here is a question of the day for you. Is it possible to choose two other symmetries as generators for this group? For example, can you use two different reflections as generators? Try to play around with this idea and see where it leads you. After watching this video, you are ready to discover new ideas such as this one on your own. This video is the first in a series on visual algebra. We will give pleasing visuals to make sense of seemingly complicated and unintuitive notions and constructions in abstract algebra. Our aim is to transform the perception and teaching of abstract algebra into something that is simple and intuitive. To join us on this journey, subscribe to this channel and watch out for future videos. Please apply a non-identity transformation to the like button if you enjoyed this video to help us conquer the YouTube recommendation algorithm and to give other fine folks a chance to discover this video. Any feedback you can leave in the comments is highly appreciated. Till next time.